Hey everybody, Dr. A here, and in this video we're going to be providing some background information on how to use the double integration method to compute flexural deformations for beams. So the double integration method, which we sometimes abbreviate as the DI method, will allow us to compute flexural deformations by solving the following second-order ordinary differential equation. Now, these flexural deformations that we can solve for are the rotation or slope angle theta and the vertical deflection of a beam, which we'll call delta. So the second order ODE, or ordinary differential equation, that we would end up solving is given here. So again, you see this is a second order differential equation, and you have delta, which is the vertical deflection, as your dependent variable, and x is the independent variable, and this is equal to m as a function of x. This is not m times x, it's m as a function of x divided by e as a function of x times I as a function of x. So m is our internal moment function, E is our modulus of elasticity, and I is our moment of inertia about the bending axis. And we're going to consider positive displacements, delta, upwards when using our standard sign convention to determine that internal moment function m as a function of x. So that means when you're doing your method of sections operations that you're already familiar with, you consider a positive moment to be one that causes the beam segment to bend concave upwards when you're looking at a free body diagram using method of sections. So oftentimes the flexural rigidity, which is the product of E times I, is going to be constant. And when that term is constant, we can drop the function of x terms from E and I. So we see that the second order differential equation of delta with respect to x is equal to m as a function of x divided by a constant EI. So you need to be familiar with that term flexural rigidity, which is just the product of modulus of elasticity and moment of inertia. And again, for prismatic members that have all of the same material composition, EI would be constant. Okay, so how do we solve this? Well, oftentimes your moment function will end up being a polynomial. Okay, it will depend on the applied loading, but ultimately you're just using method of sections to get the moment function. So our slope angle, which we're going to call theta as a function of x, will be equal to the single integral of this second order differential equation. So we'll say d squared delta over dx squared, okay? And if we substitute this term in here, we're going to write that as the single integral of m as a function of x over ei with respect to x. Now, when ei is constant, we can pull that out of the integral. So I'm going to make a note here. I'm going to say for ei constant, we can rewrite this as e times I times theta as a function of x equals the integral of m as a function of x dx. And so what I did was I pulled out the 1 over ei out of the integral, and then I cross multiplied it to the left side of the equation. So I end up with e times I times theta as a function of x. This is often a much more convenient way to express this evaluation, because you just will have the integral term with the moment function alone on one side of that equation. Now, how about the deflection or the displacement? So the deflection, which we're going to write that as delta as a function of x, is going to be the double integral of this second order differential equation. Okay, and if we substitute again the m over ei term into that double integral, we're going to get the double integral of m as a function of x over ei dx dx. Okay, and again, if ei is constant, we can rewrite this as the following. So we're going to say for ei constant, we've got ei times delta as a function of x equals the double integral of m as a function of x dx dx. Now, you might notice that the interior integral here is already being computed when you compute the slope angle. So again, the slope angle computation is the single integral of m over ei, and so that's actually the interior integral of our deflection integration. Okay, so again, you're really just taking the integral of m as a function of x twice, and that's why, again, to be mathematically proper, we have dx dx. All right, so let's talk about some attributes of the sign convention. So for the sign convention, we're going to take deflections as positive upward and rotations as positive going counterclockwise, and these are based on internal moment m as a function of x causing the beam's free body diagram to bend concave up. And this is our standard sign convention when we were learning method of sections and we were determining internal moment functions from method of sections. Another thing we can utilize when we're performing these calculations is small angle theory. So I'm going to write small angle theory is applicable. Now, if you remember, small angle theory says that theta is approximately equal to the tangent of theta, which is equal to d delta over dx, okay? And so, again, small angle theory is typically applicable whenever you have very, very small rotations. And for most applications, especially in civil engineering and structural engineering, you're going to have small magnitude rotations. Now, the next piece of this that's really important for us to be mindful of is you notice these are all what kind of integrals from calculus? These are indefinite integrals. So if you remember from calculus, indefinite integrals do not have integration limits. Notice there's no integration limits on any of these integrals, okay? Whereas definite integrals have integration limits. For example, you take an integral from a value from a to b, okay? So when you have an indefinite integral, you will develop what when you perform an integration operation? Well, you'll pop out an integration constant. So let's make a note of that. We're going to say when evaluating indefinite integrals, we will develop integration constants. Okay, that's the plus C whenever you evaluate an indefinite integrals. So how do we handle those? Well, in order to solve for these constants, we're going to say the following. To solve for these integration constants, we apply boundary conditions and or what are called continuity conditions. Okay, so boundary conditions and continuity conditions represent physical constraints on your beam or on your system. And typically those have to do with external support reactions or any kind of discontinuity along the length of the beam, okay, or of your member. So we're going to make a note here. We're going to say these are developed by evaluating slope which is theta, and deflection, which is delta, at points on the beam where we know a particular value of theta and delta. So for example, if you have a fixed connection in your beam, say for a cantilever beam, for example, at that fixed connection, we know that the displacement will be 0 and the rotation will also be 0 because a fixed connection does not allow for any deflection or rotation. So those would represent boundary conditions, okay? A continuity condition mathematically will function very similar to a boundary condition. However, continuity conditions represent situations along the length of the beam in which your slope or your displacement should be equal at a particular point when you have multiple segmented domains, okay? So when we actually get into some numerical calculations in another video, we're going to explore this idea of boundary and continuity conditions more thoroughly. So this video, again, was just meant to give you an overview and some background information on the double integration method. If you found this video helpful, please hit like and subscribe, and thanks for watching.